Hello everyone, welcome to the tutorial number 14 of IIT-JAM in chemistry, and this is the 10th lecture of the physical chemistry chapter Atomic and Molecular Structure, and the topics which are going to be discussed today are Pauli Exclusion Principle and the Hund's rule of maximum multiplicity. Before starting, we have to get acquainted with the quantum numbers. First of all, the principal quantum numbers designated as small letter n, and this is the positive integral numbers. It will indicate the quantized energy levels according to the Bohr's theory. That means this is the first orbit, this is the second orbit, third orbit, and etc. Next comes the Azimuthal quantum numbers designated as small letter L, and it depends upon n in turn as L equals to starting from 0 to n minus 1. Suppose L equals to 1, then it will have two values 0 and it will have only one value 0. If L equals to 2, then it will have two values 0 and 1. So if it has n equals to 5, suppose, then it will have five values 0, 1, 2, and 3 and 4. This way we have to write the Azimuthal quantum numbers. Now comes the magnetic quantum numbers. Here, while discussing the magnetic quantum number, we have to switch from the two-dimensional concept to the three-dimensional concept, that is from the concept of orbit to suborbit to orbital, which is three-dimensional, and it will actually give you the idea of the orientation of the different orbital angular momentum. And this L and this M in turn depends upon the value of L as starting from minus L via 0 to plus L. Suppose L has the value 1, then it will have minus 1, 0, plus 1. Suppose L equals to 3, so it will have the values minus 3, minus 2, minus 1, 0, plus 1, plus 2, and plus 3. This way we have to write the values of the different magnetic quantum numbers, and each value indicates one orbital, and each orbital contains two electrons. And these electrons are designated as their spin quantum numbers, and arbitrarily if one is given plus half, another would be given minus half according to their spin. And if plus half is having some spin, suppose clockwise, then it will have anti-clockwise spin, or vice versa. If this one is having anti-clockwise spin, then it will have the clockwise spin. The main thing is that both of the electrons should have opposite spins, therefore their spin quantum numbers should be having opposite signs. If one is plus up, another should be minus up. So these are the set of four quantum numbers, and after that, before starting the Pauli exclusion principle and the Hund's rule, we have to know the sequence of subshells, that means the suborbits. So electrons, this is the Aufbau principle, and according to this principle, electrons are placed in the lowest energetically available subshells. These are the energy levels, that is the subshells. This is here, the principal quantum number is 1, and for 1, L equals to 0, and this 0 is 1s. For n equals to 2, L equals to 1, 0 and 1 actually. L equals to 0 and 1. For L equals to 0 it is 2s, for L equals to 1 it is 2p. For n equals to 3, L has three values 0, 1 and 2. So 3s, 3p and 3d are the corresponding orbitals, and actually suborbits, not orbitals, suborbits. And then for n equal to 4, it will have 4 suborbits. N equal to 5, it will have 5 suborbits, but here in this picture only 4 are shown. 4 will work for our discussion. 5 are not required. For n equals to 6, 6 suborbits or subshells are available, but we are showing here in this picture only 3. For n equals to 7, there are 7 subshells, but we are showing here in this picture only 2. And their energy sequence actually follows the n plus L rule. If the value of n plus L is increasing, then the energy of the subshells will also increase. Suppose here n equal to 1, L equal to 0. So this value is 1. While here n equals to 2, L equals to 0. So the total summation is 2. So this will have higher energy. For this one, the summation is 2 plus 1, it is 3. For this one, it is 3 plus 0, it is 3. So for these two, we have another rule. If the n plus L value is equal for two different subshells, in that case, the subshell will, with lower n values, has lower energy. So for 3s, it is 3 and for 2p also it is 2 plus 1 3, but the n value is lower here, so it will have lower energy. Therefore 2p has lower energy than 3s, and this way, according to the direction of this arrow, the energy of the subshells will increase and the electrons will occupy from lower energy to higher energy energetically available suborbits or subshells according to this Aufbau principle. And now comes the Hund's rule of maximum multiplicity. This rule states that for a given electronic configuration, the term with maximum multiplicity falls lowest in energy. That means what? Look at this picture. Here, suppose for carbon, these two electrons are 2p electrons, but these 2p electrons will not occupy the 2px orbitals at once. It will start occupying, first of all, with unpaired spin. First it will occupy the 2px, then it will occupy the 2py. For nitrogen, it will go to the 2pz. Then the fourth electron of the 2p orbital for oxygen will pair up with the 2px electron, and here it will be completely filled up. So this is the Hund's rule. Therefore, if two or more energetically available orbitals are available, suppose p, d and f, this is not applicable for s because s has only one orbital, but p has 3 orbitals, d has 5 orbitals, f has 7 orbitals. This way, here p, d and f are given as examples. So in that case, electrons should be spread out before they are paired up. Okay, so first of all, they will be occupying the subshells, the orbitals in the unpaired spin, then they will start pairing up. Okay, and here we have calculated that overall number of unpaired electrons. Now comes the Pauli exclusion principle. This principle states that no two electrons in the one atom can have all similar quantum numbers. For example, suppose take neon atom. It has 10 electrons. So electronic configuration is 1s2, 2s2, 2p6, and it will have the set of 4 quantum numbers for each electron. For electron number 1, this is the set of 4 quantum numbers. Electron number 2, this, and up to electron number 10, this is the set of 4 quantum numbers. Look here, for these 2 electrons, principal quantum number are 1, but the remaining 8 electrons all have principal quantum number 2. For n equals to 1, L equals to 0. So for these 2 electrons, both have L equals to 0, and for L equals to 0, m will also be equal to 0. For both electrons, it will be 0, but they will occupy the same orbit, 1s orbit, with opposite spins. That is why the spin quantum numbers, if the first one has plus half, then the second one will have minus half. Now for n equals to 2, L has 2 values. One is 0, another is 1. For 0, m equals to 1, so it will be applicable for 2 electrons, but for 1, it will be applicable for 6 electrons. Because for n equals to 2, L will have the value, for L equals to 1, m will have the value minus 1, 0 and plus 1. So minus 1 will occupy 2 electron, 0 will be occupied by 2 electrons, and plus 1 will also be occupied by 2 electrons. So for 6 electrons. Now consider any set of 4 quantum numbers for any 2 electrons. Suppose take the electron number 4 and electron number 7. Okay. So for electron number 4, n are same, L are different, m are same, s are different. Okay. Let's come to electron number 8 and electron number 4. N are same, L are different, m are same, even s are also same. So anywhere they will have to mismatch. Maximum 3 quantum numbers will match, but not more than 3. All the 4 quantum numbers will never match. This is also possible that none of the quantum numbers are matching. Suppose take for example this first electron and the 10th electron. None of the 4 quantum numbers are matching. This is n equals to 1, while this is n equals to 2, L equals to 0, L equals to 1, m equals to 0, m equals to plus 1, s equal to plus half, s equal to minus half. So matching up none of out of the 4 quantum numbers is possible, and matching up any 3 out of the 4 quantum numbers is also possible, but matching of all the 4 quantum numbers out of 4 is not possible. This is Pauli exclusion principle. Now there are some exceptions of the Aufbau principle. Suppose take the chromium and copper system. Chromium is having 24 electrons and copper is having 29 electrons. So chromium should have electronic configuration according to the Aufbau principle, 4s2, argon 4s2 and 3d4, while copper should have the electronic configuration argon 4s2, 3d9, and the electrons according to the Hund's rule would occupy like this. 4s will be occupied by 2 electrons and 4d will be occupied by 4 single electrons, unpaired electrons, while in case of copper 4s will be orbital will be paired up, whereas the 4 of the 5 d orbitals will be paired up and the 5th orbital will remain unpaired. But according to Aufbau principle, these arrangements are not allowed, and these are exceptions. This electron will occupy here in order to make maximum multiplicity of unpaired electrons. So because half filled d orbital is more stable than this arrangement, here also this electron will move here to pair up this unpaired electron, because completely filled d orbital is more stable than this arrangement of 9d electrons. Okay, so these are wrong for chromium. So this is the correct arrangement, and this arrangement for copper is also wrong, and this is the correct arrangement. Okay, this is the Aufbau principle exceptions. And now comes to the 23 electron systems. Vanadium has 23 electrons and it has the electronic configuration argon 4s2 3d3. Similarly, manganese has 25 electrons and it has electronic configuration argon 4s2 3d5. But if you take 2 electrons from manganese, then it will become a 23 electron system. Then it should have electronic configuration like this, but it will not happen in case of this ion. For ions, you have to take the 2 electrons from the outermost orbits. That means you have to take the 2 electrons from here, not from here. So it will not be 4s2 3d3. It will be rather 4s0 3d5. Now move on to the questions. The correct valence shell electronic configuration of the element with atomic number 22 is, out of these 4 options, which is correct? So let's discuss the answer here. Argon has 18 electrons, so 1s2 2s2 2p6 3s2 3p6. These are the arrangement of 18 electrons. Argon, after argon we have 4 electrons, so for the next 4 electrons the available subshells are 4s and 3d, and therefore the correct electronic arrangement should be 4s2 3d2 after argon. Therefore the correct option is option number A. And this question came in IIT-JAM 2007. Now move on to the next question. Which of the following set or sets of quantum numbers is or are not allowed here? So here are 4 options. So let's check which set of the quantum numbers are correct or which set are incorrect. So first of all, the first option, where n equals to 3, l equals to 2 and m equals to -1. M is also sometimes written as ml and s is also sometimes written as ms. Now for n equals to 3, l has 3 values, 2, 1 and 0. And for l equals to 2, m has 5 values, -2, -1, 0, +1, +2. So all these values are here allowed, 3, 2 and -1, 3, 2 and -1. So this one is correct. Now B is looks here incorrect. Why incorrect? Look here, B, n equals to 4, l equals to 0, m equals to -1. Now let's check. N equals to 4, for n equals to 4, l should have 4 values, 3, 2, 1 and 0. Now here it's given that m equals to -1, but whether it is possible for m equals to -1 if l equals to 0? No. For l equals to 0, m should have only one value, 0. If here in place of l there had been 1, then the -1 value would have been valid. So this one is incorrect. Now option C, here n equal to 3, l equal to 3, this one is incorrect, because for n equals to 3, l has 3 values which are 2, 1 and 0. There is no value which is equal to 3. So first of all, it is rejected due to this value. Hence this one is incorrect. Now move on to the last, n equals to 5. So for n equals to 5, l should have 5 values, 4, 3, 2, 1 and 0. Now here it's given m equals to plus 2. For L equals to 3, m can have 7 set of magnetic quantum numbers, that is minus 3, starting from minus 3 via 0 to plus 3, that is minus 3, minus 2, minus 1, 0, plus 1, plus 2, this one matching here, and plus 3. So this is correct, 5, 3 and plus 2. So the correct option, the sets of quantum numbers from option B and C are not allowed. Okay, so that's all for this chapter. Overall 38 number of questions have been discussed here. Now next we are going to, the next chapter we are going to start is the gaseous state. But before extending my thanks to all of you, that all the links are available in the description box below. Links means the links of the previous lecture, the link of the next lecture, of each lecture. They're all available in the description box below. And it will be better if you browse the playlists of this channel, which is also available in the playlist tab. Okay, just type my name and go to the channel, then go to the playlist tab. There, apart from all these IIT-JAM chapters, you will get so many other chapters also, like thermodynamics, then solid state. So many chapters are available there. So just please browse the playlists also. So thank you, have a nice day, and all the best for your IIT-JAM